describe about a memory, basically there are three types of memory. Basically there are three types of memory. Number one type is internal, you can note it down, internal processor memory. Internal processor. Number two is main memory. Main memory. And number three is auxiliary memory. Auxiliary memory. So basically there are three types of memories. There is internal processor memory, there is main memory, and there is auxiliary memory. We know the job of memory is to store the data in the form of zeros and ones. So when I talk about the let's start with the main memory. Let's start with the main memory. The job of main memory is to store the data and programs. Store the data as well as programs. So what type of data and programs will be stored in the main memory? The data and the programs, whatever whatever system wants to execute, or whatever a programmer wants to execute, that data and program will be loaded into main memory. So if let's say I'm starting the computer system, and I have I want to use the Excel application. Then that whatever data and programs required for the data and program required for this Excel application will be loaded into main memory. So whatever data and programs related to Excel will be loaded into main memory, because I want to execute Excel application. So you can say that the name itself says main means it is important one. In what ways it is important one? Because it holds the data whatever user wants to execute, or whatever programmer wants to execute. If programmer wants to execute some task, some program, then that program will be first loaded into main memory. वो कहाँ पर load होगा? That program will be loaded into main memory. So when I look at the picture of processor and memory, so you can imagine that this is my processor, and this is my main memory. So we have a processor. What is the job of processor? The job of processor is to execute the data and program. Which data and program it is going to execute? Whatever data is loaded into main memory, first we need to transfer that data and programs into the processor. Main memory, we need to shift the data from the main memory to the processor, and then processor will execute, and processor will shift the result of that data to the main memory. Getting? So you can here you can clearly see that this memory is situated apart. That means it is situated, it is not that much in a closer way. That means every time if a processor wants to execute something, processor needs to go back to the memory, get the data, and then execute it. So this processor and memory are the two different devices. They are not close to each other. Actually, they are far away from one another. They need to go, the processor need to go to the memory, and then to execute something, and then data will be loaded from the main memory to the processor, and then processor will execute. Getting? But this may happen that my computer system is not only having the Excel application. My computer system is having number of different applications, number of different softwares loaded in my computer system. One of the software may be Word, one of the software may be Excel, one of the software may be a gaming application, one of the software may be a PDF. So whatever softwares you have in your system, whatever softwares you have installed in your system, it is not always the case that we will need all these softwares. It is not always the case that we will need all these softwares at a time to execute. This will never happen. We never need all the software of your computer system at the same time. Sometimes we may max at we may need two softwares, or we may parallelly execute 4 to 5 applications, or we may parallelly execute 10 to 20 applications. But let's say if I have 100 softwares already installed in my computer system, 100 softwares installed in my computer system, but instead of 110, I just need, at this point of time, let's say I need only 15 softwares. This is also a maximum number. Let's say I need to execute only 15 applications. Then these 15 applications which I need to execute currently, these 15 applications, so whatever data and programs, whatever data related to these 15 applications will be loaded into the main memory. Why it is loaded into the main memory? Because I need to execute them. If I need to execute any program, then that program will be loaded into main memory. Then what about these softwares? What about these softwares? These softwares, that means the 110, the total number of softwares, 110 softwares are stored in a separate memory, and that memory is called as auxiliary memory. That memory is called as what? Auxiliary memory. So again, I can say which type of memory, what is the job of auxiliary memory? Can you say that? That the job of auxiliary memory is to store all data and programs, all the data and programs which are not needed currently, which are not needed currently. That means I don't want to execute that program. Then if I don't want to execute any program right now, then all the data will be placed in the auxiliary memory. All the data will be placed in this auxiliary memory. Getting? So whatever data you want to execute, whatever data you want to execute, that will be loaded in. Again I'm explaining that this is our processor. This is our processor. Entire data and programs, all the data and programs, all the data and programs will be stored in the auxiliary memory. All the data which are not needed. So let's say it is having total 10 programs. Let's say this auxiliary memory has total 10 programs. Then out of these 10, with this auxiliary memory, I have main memory also. So this is my main memory. This is my auxiliary memory. Job of auxiliary memory is to store the entire data and programs which are not needed currently. But out of this auxiliary memory, if I want to execute this application number 1 and application number 2, these two application if I need, then these two application will be loaded from the auxiliary memory into the main memory. So now main memory will have two programs, 1 and 2. Why I have loaded 1 and 2 only? Because currently I wish to execute which programs? Program number 1 and program number 2. Therefore, I will bring all the data out of this complete data in the auxiliary memory. Out of this complete data in the auxiliary memory, which data I want to execute? I want to execute application number 1 and application number 2, or you can say program number 1 and program number 2. So this program 1 and program 2 will be loaded into main memory, because whatever data we need to execute, we need to load it into the main memory. And from main memory, this will be loaded into the processor. From the main memory, this will be loaded into the processor. two data, that means 1 and 2 will be loaded into the processor, and here processor will execute that data. Here processor will execute that data. Getting or not? What the concept that we have we have three types of memory, or broadly we can classify a memory into three categories: auxiliary memory, main memory, and the third one is internal processor memory. The third one is internal processor memory. So till now we have seen auxiliary memory, we have seen main memory, we have seen auxiliary memory, we have seen main memory. But what about this internal processor memory? What about this internal processor memory? When it comes to internal processor memory, it is a memory used by the processor itself. The memory used by the processor itself is called as internal processor memory. So, processor needs some kind of memory to store the data temporarily. To store the data temporarily, processor itself has some sort of memory. So what are those memories which are used by processor? The memories used by the processors are registers, and second one is cache memory. Registers and cache memory. So what is, let's see what is cache memory. Let's see what is cache memory. So cache memory is the memory which is placed, or which is situated at the processor itself. At the processor itself. This means, again here I am making some changes. So earlier my processor, this was my processor, this is my processor. Now this processor itself make use of some memory, and the one of the type of that memory is register, and the another memory which is used by the processor itself is cache memory. Used by the processor itself is cache memory. So what is the job of register? First we'll see. Registers are nothing but the small devices, small electronic devices. The job of these registers is to store the data. Job of this register is to store the data in the form of zeros and ones. These registers are used by processors only. That means processor make use of these registers for its temporary storage. Then what is the next memory? That is cache memory. What is its job? See, we have seen that the entire data and programs will be stored in which memory? Auxiliary memory. Now out of this auxiliary memory, the data we wish to execute, that will be placed in which memory? That will be placed in the main memory. The data and programs we wish to execute currently, that data and programs will be placed into main memory. Now imagine that if every time I am making use of these two applications only, if every time, let's say out of these two, the most needed application is application number 1, it may happen that one of the application or few applications are widely needed or frequently needed. So whatever frequently needed application, if I have out of this, I am executing 1 and 2 program, software number 1 and software number 2, or you can say program 1 and program 2. Out of this, I know that program number 1 is frequently used. Still, I need to go, this processor need to go to the main memory. again load the data from for this one and then execute it here and then execute it here. So every time processor has to take this to load the data for which application, for application number 1 from this main memory. So it is time consuming. So the job of cache memory or job of this cache memory is to load the data, which is frequently executed or which is frequently needed. That data out of this complete main memory, from this main memory, it will take the data which is frequently needed. So which data is frequently needed? Number 1 application or first program data is frequently needed. So that data will be stored into cache memory. So what data and programs are called cache will hold? Now the cache will hold the data for program number 1. So now if processor wants to execute the data for program 1, it will not have to again visit to the main memory. Why? Because the data is already in his corner itself, in his side itself. इन इट साइड डेटा ऑलरेडी प्रेजेंट है. कहां पर? प्रोसेसर साइड में ऑलरेडी डेटा प्रेजेंट है. it does not needs to visit to the main memory. So the here memory read operations has been decreased. If you decrease the memory read operations, that means the time to execute that program will be within a fraction of time we will execute this. Why? Because every time I will not go into the main memory and I will load the data from program number 1. What I have done, I have taken that data and loaded where? Into the cache memory. I loaded that into cache memory, and whenever processor needs that data, it will directly take it from its side. It will directly take it from the cache only. It will not visit to the main memory. So that is the job of cache memory. We'll see the memory hierarchy. Hierarchy means what? Hierarchy is nothing but the levels. Hierarchy indicates what? Levels. So this pyramid shows that at the top of this hierarchy we have register memory. Then the next level is cache memory. Then the next level is main memory. Next level is magnetic disk and magnetic tape. So register memory and cache memory are placed where? Register memory and cache memory are placed where? These two memories are actually placed at the processor side. They are actually placed at the processor side. So we have right now we have seen that these register memory was placed. This register and cache was placed in the processor side. So we can call this register memory and cache memory as internal processor memory. We can call this as internal processor memory. The next memory in the hierarchy is main memory. This main memory is also called as primary memory. What is its job? Its job is to store the data which I needs to get, whatever needs to be executed by the processor. So that data will be loaded into the main memory. So this main memory resides central to the computer system. And then the next you can see magnetic disk and magnetic tape. These two memories are referred as auxiliary memory. Getting the definition of auxiliary memory? Entire data, entire programs, all the data, all the softwares which are not needed currently will be stored where? In the auxiliary memory. So what type of memories can be used in this case? Magnetic disk and magnetic tape. Next we will see that what is the characteristic of each and every memory. That out of these each of this memory is at some level. one at the above level, next at the next level, then you can say that this is L1, then this is L2, or you can say this is level 3, this you can say level 4. So likewise you can differentiate. So memory at the top is the register memory. So let's talk about this register memory. This register memory is the fastest memory, fastest memory, fastest memory. So this is the fastest memory. Again, the cost of this register memory is very high. The cost is very high. The cost required for this type of memory is very high. The third characteristic that it has is it is having the storage capacity. It is having the storage capacity of very low storage capacity. Very low storage capacity. Very low storage means how much data it can store. A register can store the data in bytes. A register can store the data in bytes. So that means it is not storing enough information. It is only storing the data in bytes. That means either 8 byte, either 16 bytes or 4 bytes. So the amount of memory used or stored by the register memory is very less. Next comes the cache memory. Next comes the cache memory. The cache memory is slower than the register memory. It is slower than the register memory, and it can store the data in KBs. It can store the data in KBs. That means here the storage requirement or the storage space is higher than who? Higher than the register memory. The storage space is higher than the register memory, but they are slower than register memory. When I say slower and faster, then I am actually talking about memory access time. Then I am talking about the term that is memory access time. What is memory access time? The time required to fetch the data from the memory is called as memory access time. The time required to fetch the data from the memory is called as memory access time. So the memory access time required for register memory is very less. That means it requires very less time. So therefore I can call it that it is the fastest one. Then the cache memories are slower than the register memory. That means the memory access time required by the cache memory will be greater than the memory access time required by the register. So I can say this clearly that this register memory will have the memory access time lesser, then this cache memory will have the memory access time greater than the register memory. Next comes the main memory. The main memory is again slower than the cache memory. It is slower than whom? Slower than the above one, slower than the cache memory. It is slower than cache memory. Then it occupies more data. That means storage space is higher than the cache memory. So this main memory, we can store the data in the main memory in the GBs. In GBs, we can store the data in main memory as GBs or MBs, mostly GBs. But it is slower than the cache memory. And as well as this main memory is also less cheaper than cache memory. So cache memory is having more cost than that of main memory, and register memory is also having more cost than that of a cache memory. Next comes the magnetic disk and magnetic tape. These two memories can store the data in GBs or in TBs or PBs. That means it can store the data in terabytes or in the petabytes. In the terabytes or in the petabytes. So you can say that again here these two memories, that is magnetic disk and magnetic tape. These memories are able to store lot of information. That means storage space is high, but their cost is low. Storage, high storage space, very low cost, but they are very slow. They are slowest. They are slowest in the memory hierarchy. They are slowest in the memory hierarchy. So if I show you with the help of the arrow, so here you can see that this is the increasing order of excess time ratio. Excess time ratio means this, here the memory access time will be highest. Here the memory access, magnetic disk will have the highest memory access time. The time required to fetch the data from the magnetic tape is higher. That means it is slowest. Then the next is magnetic disk. That means they are faster than whom? They are faster than magnetic tape. Then next come main memory. Main memory is faster than magnetic disk. Then next come cache memory. Cache memory is faster than so here main memory is faster than the magnetic disk. Main memory is faster than the magnetic disk, and then cache memory is more faster than the main memory, and register memory, they are the fastest. So you can say that if I will draw a line, if I draw a line one for the memory access time, this is my memory access time. So it is in the increasing order. And when I draw a line for cost, again it is in the increasing order. I can draw a line for a cost, which indicates that register will have the highest cost, cache memory will have the next highest cost, main memory will have the next highest cost. Then I have, if I draw a line for storage space, then the storage space is in the decreasing order. That means this magnetic tape is able to store more amount of data as compared to magnetic disk. Main memory will store less amount of data as compared to magnetic disk. Cache memory will store less amount of data as compared to my main memory, and register memory is able to store very few amount of data. So we have differentiated this on the basis of cost, storage capacity, and memory access time. Cost, storage capacity, and memory access time. So you have to understand this very well, because these all will be important while solving the questions, that which memory will have how much cost, storage, and access time. So we have seen what is main memory, the memory unit that communicates directly with the CPU. Is called the main memory. Then it is the large and fast memory. What is the job of main memory? It is used to store the data. Which is to be executed. Then auxiliary memory, it is used for the backup storage. Why I am calling it as backup storage? Because it is used to store all the data. So the data which is not being currently executed, or which does not needed right now, all that data will be stored in the auxiliary memory. Then we have cache memory. We have also seen that instead of going to the main memory repeatedly to access some information, if I have some amount of data which I needed many times, or if I need it currently, then I will load that data where into the cache, into this cache memory. So from this main memory I will load the data into the cache memory. Which data will be loaded? Which is needed frequently. So instead of going to the main memory, processor will itself make use of this cache memory. So data or contents of the main memory that are used again and again by the CPU are stored in the cache. You can see, so that we can easily access that data in a shorter time. In a shorter time. That is the job of cache memory. So here you can see the hierarchy representation, how that memory hierarchy is there in the computer system. You will see that this is our processor. This is our processor, CPU. CPU is directly dealing with whom? Cache memory. CPU is dealing with whom? Cache memory. And then we have main memory, we have magnetic disk and magnetic tape. So here we have all the data. Here we have all the data, all the backup data. If main memory wants to execute some data, it will load it from this magnetic tape or magnetic disk into the main memory. If I want to execute some information or some task, the data will be loaded from the auxiliary memory into the main memory using some sort of input output processor. So with the help of input output processor, main memory fetches the data from the magnetic tape and the magnetic disk, and then it transfer its data to whom? To the CPU in order to execute it. Now if there is some data in the main memory which I needed again and again, then that data, CPU will take that data and it will load it into the cache memory. It will load it into the cache memory. So data from the main memory will be loaded where? Into the cache memory. And instead of going back, if I need to execute the data, then it will first search into the cache memory for the required data into the cache memory, and then if it is not found, then it will go into the main memory. Now here comes again the next important one. So now we will see the important concept, that is hit ratio and miss ratio. Memory hit and memory miss. What is called as memory hit? Again, it is very important topic, memory hit and memory miss. So we know that we have our processor, and this processor is holding the cache memory. This process is holding the cache memory, and then we have we have main memory. We have main memory. So data is loaded into the main memory. Whatever data I needed, whatever data need to be executed, this is loaded into the main memory. And if out of this some data will be loaded into cache memory, because its size is less. Its size is less than the cache memory is always having the size lesser than the main memory, but it is faster than the main memory. So cache will take the data which is required again and again. So what processor will do? If a processor wishes to execute some instruction, the processor will first search into the cache memory. Processor will first search for that required data into the cache memory. If that data is found in that cache memory, then processor will execute that data there itself. There itself. So processor wants to execute some data, processor wants to execute some program, processor will search that required data into cache memory. If that data is found in the cache memory, then we call it as memory hit. Then we call this operation as memory hit operation. So you can see the definition. When the CPU refers to the memory and finds the word in the cache, then it is set to produce a memory hit. So processor wants to execute some data. Processor will initially search into its own memory, that is cache memory. If the data is present over there, then we call it as memory hit. If the data, the required data for which the processor is searching for, if that data is not present in that memory, then processor will move to the main memory. Then the processor will move into the memory because the required data was first searched into the cache memory, but it was not found over there. The required data was not found in the cache memory. Then we call this as memory miss. We call it as memory miss. Once again, note it down. What is memory hit and what is memory miss? Memory hit means processor will search for the data, required data, into the cache itself. If the data is found, then it is called as memory hit. If the data is not there in the cache memory, then it has to move where, it has to search where, it has to search in the main memory. So if the data is not found in the cache memory and it is in the main memory, then it mark it as memory miss. Memory miss. So again this is, you can read this. If the word is not found in the cache, it is in the main memory, then it counted as a miss. So many times the questions are based on this memory hit and memory miss. So here you can create, or we can define the hit ratio. The hit ratio can be calculated as number of hits divided by hit plus miss. This is the formula for calculating the hit ratio. Where the hit ratio can be calculated by, इसमें hit तो calculate होंगे, हो ही रहे हैं, साथ में that hit ratio कैसे calculate होगा, hit divided by hit plus miss. So you can note down this hit ratio. Next, how many types of memory organizations we have? So totally a memory can be organized in two different ways. Number one way is simultaneous access memory organization, and number two is hierarchical access memory organization. Hierarchical. So here in this diagram you can see that processor is connected with the memory, with the two memories. One memory is a level 1 memory. First memory is level 1 memory. Second memory is level 2 memory. So when I say level 1 and level 2, again come back to our memory hierarchy. Where I can say that this is my level 1. Assume that if I am saying that register memory is level 1. and cache memory is level 2. Then how will you differentiate it? How will you differentiate it? You can differentiate it this in this way that L1 L1 will always have the memory access time. The memory access time of L1 will always be smaller than whom? Than the memory access time of L2. That means L1 is always faster than whom? L2. This is the first condition, that L1 is always faster than L2. The second condition is that the storage space, that means the amount of storage space, will always be lesser in the L1, will always be lesser in level 1, and it will be greater in level 2. Greater in level 2. So if I say that this is L2 and this is L3, then in this case L2 will have this cache memory L2 and L3. Then L2 will have memory access time lesser memory access time than the L3, and the storage will be less, and the storage will also be less. Storage will also be less. So again here you can see, if I am talking about simultaneous access memory organization, there are two types of level. If here as an example, it is given that there are two levels of memory, level 1 and level 2. Level 2 means what I will write? Memory access time. जितना टाइम लग रहा है एक्सेस करने के लिए, किसको एक्सेस करने के लिए? L1 will always be lesser than the memory access time required for L2. Required for L2. Then the second is, this will have the storage cost. Cost will be higher than the level 2. So level 1 will always have the higher cost than level 2. What about the storage space? The storage space will always be lesser. Here level 1 will always have the less storage space than the level 2. Than the level 2. Getting? So every time if I am talking about level 1, level 2, getting their meaning? Level 1, what is the job of L1 and what is the job of L2? So here a CPU can organize the memory. A CPU can organize, or it can access to the memory in two different ways. A CPU can have access to the memory in two different ways. Number one way is simultaneous access. Number one method is simultaneous access. So you can see that this is the example of simultaneous access, where if CPU wants to search some data, and if there are two levels of memory, then CPU will start searching at the same time in the level 1 as well as in the level 2. Level 1 and level 2. So CPU, whenever I say simultaneous access, the name itself says that CPU will try to search for the required data. If CPU wants to search something, if CPU wants to search some data, then we have two memories. We have level 1 memory, we have level 2 memory. We have some data, we have the data stored here in level 1 also. We have some data stored in level 2 also. In level 1, we have some data stored in level 1 and level 2. Then what CPU will do? CPU will start searching for the required data at the same time in level 1 as well as in the level 2. Getting? Now when it comes to hierarchical access memory access organization, then in this case, CPU will first search in the level 1. Will first start searching in the level 1. If the required data is not there in level 1, then only it will start searching in the level 2. Then only it will start searching in the level 2. Got it? what is simultaneous access memory organization and what is hierarchical memory access organization. So आप मेमोरी को ऐसे ऑर्गेनाइज कर सकते हो. We can organize the memory in two different ways, either in simultaneous or in hierarchical. When I say simultaneous, the data will be see if the required data will be searched in both the levels or in all the levels at the same time. Whereas in hierarchical, first we will search the data in level 1. If it is not found, then we will search in level 2. Let's say if it is having level 3 and the data is not found in level 2, then we will start searching in the level 3. We will start searching in the level 3. And if this structure is having one more level, let's say if it is having level 3, then the entire search will be performed in all the levels simultaneously. All the levels simultaneously. That means CPU will search in level 1, level 2 and level 3 at the same time. So you can see all the levels of the memory are directly connected to the CPU. Whenever CPU requires any word, it starts searching for it in all the levels simultaneously. And when it comes to hierarchical, when CPU requires any word, it first searches for the level, the data in the level 1. If the required data is not found in level 1, then it starts searching for the word in the level 2. If not required, if it is again not found in the level 2, then it will search in the level 3. And if not, then again so on, whatever number of levels you may have. So, so assume that this is my CPU, and here I am having level 1, level 2 and level 3, and I am searching for the data in all the levels simultaneously. I am searching for the data in all the levels simultaneously. Then here T1 is the access time of level 1. T1 is the access time. This is my L1, this is my L2 and this is my L3. So we have some terms, we have some keywords associated with this. In order to solve the numerical based on this, first we need to discuss some of the terms related with this. So we have 4 terms related with level 1. 4 terms related with level 1. Number 1 is T1. What is T1? T1 is the access time of T1 is the access time of whom? L1. Then S1 is the size of L1. C1 indicates what? Cost per byte of level 1. And H1 is the hit rate of L1. Got it? What is hit rate? What is miss rate? We have seen it just now. So similarly, for level 2, there are again 4 terms: T2, S2, C2 and H2. What does T2 indicates? T2 indicates the time required or the access time for level 2. S2 indicates size of level 2. C2 indicates cost of level 2 and H2 indicates hit rate of level 2. So what things we know already? The thing we know already is T1 will always be lesser than T2. How come? How come? How can I say that T1 is lesser than T2? Because I always says that level 1 and level 2. Out of this level 1 and level 2, if I imagine it in the hierarchy, level 1 is placed here and level 2 is placed here. So this level 1 will always be faster than the level 2. So the time required to get the information from T1 will always be lesser. That means it will be very less time will be required to access the data from level 1. Whereas the time required from T2 will be greater. Similarly, what about the size? How much data will be stored? So always the size of S1 will always be smaller than the S2. That means S2 will always hold the data greater than the S1. What will be the cost? cost of C1 will always be greater than the cost of C2. Will always cost, that means the cost of this level 1 hierarchy will always be greater than the level 2. So C1 will be greater than C2. And what about this H1 and H2? That will depend, H1 and H2, that will depend upon the hit rate, that where the data is available. If the data is available in the L1, then the hit rate will be, if the maximum data is available in L1, then we can say that hit rate of L1 is more than the hit rate of L2. So again, important one, if I am going for the two level memory hierarchy, so here I am having level 1 and level 2. So it is two level memory hierarchy, which is making use of which type of organization? Simultaneous memory organization. That means if the CPU wants to search the data, it will search for the data in level 1 and level 2 at the same time. So CPU will search in level 1, CPU will search in level 2 at the same time. So the T average, that means that the average time required to access the information. Again, it is very important formula. The average time required to access the information will be number 1, H1. H1, what is H1? It is the hit ratio of whom? Level 1. What is T1? The time required to access that information. So what we will write, that where the information is, how we can calculate it, how this formula is represented. First we will write H1, that means hit ratio of level 1 multiplied by the time required by the level 1. Hit ratio of level 1 into time required by the level 1 plus, if I am searching for the data, then if I found the data over there, if the CPU is searching for some data and that data is available in level 1, then hit occurred, that means H1 occurs, and within how much time? Let's say T1. So this is my average time. H1 into T1. But this is only, I'm here I'm just assuming that my data is, if I will just only write this and if I will not write this, this means that I found the data in level 1. This only means that I found the data in level 1. But it is not always the case. It may happen that I am searching for the data in level 1 and level 2, and it happens that data is not available in level 1. If the data is not available in level 1, then it is guaranteed that it is available in level 2. So for this, here I am first multiplying the miss ratio. What is the miss ratio? Or the penalty, you can say. So here 1 minus H1. 1 minus H1. Why I am writing 1 minus H1? This 1 minus H1 is actually the miss ratio or the miss rate. Miss rate means, let's say I am having the probability of 1. And here there are two things, L1 and L2. So what is the probability that I will get the data here? What is the probability? 50% probability is there. There is probability of 50% that a data might either be in level 1 or either be in the level 2. So how I can calculate it? Here I am assuming that I found the data in I am searching for level 1 and I found the data. So this is only the hit ratio of L1. It may also happen that I search for the data in, I completely searched the level 1 but I didn't found anything. Then this is the miss ratio. How I have calculated it? I have written it 1 minus H1. 1 minus H1 into T2. Why I am writing 1 minus only? Because the probability of getting the data is 1. We are measuring the probability in terms of 1. In terms of 1, or you can say 100%. 100%. So here I am writing that whatever hit ratio of previous minus that H1 will be calculated as the miss penalty into 2 into T2. So this is the formula for simultaneous memory access organization, level 2 memory organization. Now next, what will be the average formula for level 2 memory organization, but this time it is having hierarchical access memory organization. Again, we know what is hierarchical memory or access organization means. First CPU for search for the data in level 1. If it is not found over there, then only it will search in the level 2. So again the formula is H1 into T1. This indicates what? That we were searching in level 1, and we got the data. So this is hit ratio for L1. This is the time for L1. But after searching the data in level 1, if that data is not there, then I will move towards where in the level 2. So here I will have the hit as well as I will have the miss ratio. So miss ratio will be calculated as 1 minus H1. 1 minus H1 is the miss ratio. Then next is T1 plus T2. How much time here we are adding? We are adding the time required for T1 and T2. Why I am adding the time T1 and T2? Why I am adding the time T1 and T2? Because I'm going to this level 2 if the data is after completely searching the level 1, after completely searching the level 1. But in previous case I am searching for level 1 and level 2 simultaneously. So it may happens that a data is present in level 2. I got the data in level 2. So the time required for level T1 will not be added in this time. During this time, it will not be added. So this is the formula. You can note it down. Similarly, if I have a 3-level memory organization, that means instead of 2 levels, I am having 3 levels, where H1, H2, H3 indicates the hit ratio of L1, the hit ratio of L2, and hit ratio of L3. Then the formula is H1 into T1 plus H1 1 minus H1 into H2 into T2 plus 1 minus H1 into 1 minus H2 into T3. So this is the formula for average access time in level 3 organization. In level 3 organization. Next, again the hierarchical, but this time I am having how many levels? Level 3. So again the formula has been modified. You can see H1 into T1, then 1 minus H1 into, then here 1 minus H2 into T1 plus T2 plus T3. So you can see the complete formula for level 3. Again the formula has been modified for level 3. So we'll try to solve some of the questions. So this is the question asked in GATE IT 2004. Consider a system with two level caches. Access time of level 1 cache, level 2 cache and main memory are 1 nanoseconds, 10 nanoseconds and 500 nanoseconds respectively. The hit rates of L1, level 1 and level 2 caches are 0.8 and 0.9 respectively. What is the average access time of the system ignoring the search time within the cache? So what is asked here? The question is asking for average access time. Average access time. Again, we will read the question first. Consider a system with two level caches. Access time of level 1, that means we have level 1 cache, then we have level 2 cache, and then we have main memory. So here we will try to draw a diagram that we will have a CPU. So this is my CPU. And how many cache are there? Level 1 and level 2. So here I am writing cache memory, but this is my level 1. Again, I am having next cache level, level 2. This is also the cache memory. And finally, we are having the main memory. So here I am writing main memory. So CPU is, there is CPU and there are three levels of hierarchy. Level 1, level 2 and level 3. There are two levels of cache. That means cache is of two level. So we have level 1 cache, we have level 2 cache, and finally we are having main memory. So how much memory organization it is? Actually it is level 3 or memory organization that we have seen previously. Level 3 memory organization. But so actually we are having three level organization. Here level 1 is our cache memory 1, level 2 is our cache memory 2, and level 3 is our main memory according to our example. But what type of organization it is? Whether it is a simultaneous memory access organization or whether it is a hierarchical memory access organization, this is not mentioned in the question. Again, read this. So whether I should implement it, I should draw in this way, I should draw it in this way, or I should have in this way. This is a big question. That this is my cache memory, this is my cache memory, and this is my main memory. So whether this question is making use of this memory organization, that means simultaneous, or whether it is having the hierarchical memory organization, we need to see this. So many times it happens that the type of organization is not mentioned in the question. The type of organization is not mentioned. In this question also, the same thing, the type of organization is not mentioned. Then which one to assume or which one to make use of? Then if it is not mentioned, then always calculate in both the ways. Calculate in both the ways. Calculate the average access time by using this method also, and calculate the average access time by using this method also, and you will see the options. One of the option will be there and that will be assumed as correct. If not, then most preferably they are using this hierarchical memory organization. Hierarchical memory organization, that means every time we will make use of this. We will make use of this hierarchical memory organization. That means first we will search in the cache memory. If it is not found, then we will search in the next memory. If it is not found, then we will search in the main memory. So here is the solution. Which type of memory organization we will make use of? Either this one or the hierarchical. Then we need to make use of the formula. So here I have solved this with the help of simultaneous memory organization. Simultaneously memory access organization का यूज करके हमने ये फॉर्मूला बनाया है. This formula is already given. Simultaneous will come to this simultaneous memory organization, and you will see the formula. The system will look into the cache memory. If it is not found in the cache 1, then cache 2 will be searched, and then further in the main memory. That is, if it is not found in the cache 2 also, then it will search in the main memory. So how we will indicate this? Here H1, hit rate of level 1. Go to the question. Hit rate of level 1 is given as, hit rate of level 1 and level 2 are 0.8 and 0.9. You can see hit rate of level 1 cache is 0.8. Hit rate of level 2 cache is 0.9. T1 is the access time for level 1 cache, and in the question it is given that it is 1 nanosecond. T2 is the access time for level 2 cache, and it is given in the question that it is 10 nanoseconds. HM and TM are the hit ratio of main memory and access time for the main memory. It is also given. Why I am writing this hit ratio of main memory as 1? Again we will go to the question. Only the hit rate of level 1 and level 2 caches are given. Level 1 is having 0.8 and level 2 is having 0.9. So again I told you that first I will search in this level 1. If it is not there, then I will search in the level 2. If it is not there, it means it is definitely present where in the level? It is definitely present in the level 3. That means the hit ratio of level 3 will be 1. Hit ratio of level 3 will be 1. Whereas the hit ratio of that, we are counting in terms of ones. We are counting in the probability of 1. 1 की 100% प्रोबेबिलिटी. तो 100% में से 80% प्रोबेबिलिटी कहाँ पर है कि लेवल 1 में मिलेगा. देन 90% प्रोबेबिलिटी कहाँ पर है कि लेवल 2 में मिलेगा. अगर इसमें नहीं मिला तो गारंटीड है 100% प्रोबेबिलिटी वो कहाँ पर मिलेगा आपको, लेवल 3 में मिलेगा ही मिलेगा. Here hit rate of level 2 cache is 0.9 according to question. Hit rate of level 1 cache is 0.8 according to question. But when it comes to hit rate of main memory, it is 1. Why? Because definitely अगर level 1 में नहीं है, level 2 में नहीं है, तो डेटा guaranteed है कि कहाँ पर होगा, मेन मेमोरी में श्योरली ये प्रेजेंट होगा ही होगा. Therefore rate of main memory is 1. So here we applied the formula average access time. Here you can see the formula H1 into T1, then 1 minus H2 into T2, then 1 minus H1, 1 minus H2 into H1 and HM into TM. So this is the formula that I have shown you. And according to it, the average access time calculated here is first 0.8 into 1, 0.2 into 0.9 into 10, then 0.2 into 0.1 into 1 into 500 nanoseconds, and here I got the result as 12.6 nanoseconds. So this is the correct answer for the average access time. So you can try for this question also. You can try for this also. You can note down the question. These two questions were asked in get access time. Again I'm here reading the question. Access time of main memory and the cache memory in a computer system are 500 nanoseconds and 50 nanoseconds. That means it is how much memory level organization it is? 2-level memory organization. So we have a CPU and we have level 1 and we have level 2. We have level 1 and level 2. One is the cache memory and another is the main memory. So next, what is given? Access time for the main memory. That means in a computer system is 500 nanoseconds. So let's imagine, let's say this is my T1 and this is my T2. So to the main memory, I am assuming that it is T2, and to the cache memory, I am assuming it as T1. So again, read the question. Access time of main memory and the cache memory in a computer system are 500 nanoseconds and 50 nanoseconds. So this means that main memory T2 is the T2 requires how much time? 500 nanoseconds, and T1 requires 50 nanoseconds. It is estimated that 80% of the main memory requests are for the read and rest for the write. Hit ratio for read access only is 0.9 and write through policy so that means here my C1 is, and here is my C2. Here I am calculating the H1 and H2. So H1 is 80%, and if the data is not there in the cache memory, then definitely it will be there in the main memory. So we have to apply the formula and we need to calculate the average time for the main memory in both, that is in the simultaneous, where both caches, both main memory and caches are updated simultaneously. So this is accessing which type of memory organization it is having? Simultaneous memory access organization. So we'll see the formula. Simultaneous. So this formula will be used to calculate the average access time. Next we will see again the important topic, that is locality of reference. We will see the important topic of cache memory. So cache memory actually works on the locality of reference. It works on the principle of locality of reference. What is this locality of reference that we will see? So we know that this is our CPU. This CPU makes use of this cache memory, and then it has the main memory. So CPU, if CPU wants to search the data, so it will first search into cache memory. If it is not found, then CPU will search for the main memory. So this is the process. So we'll see how this cache memory works, or what is the principle behind cache memory. The principle behind cache memory is it works on the principle of locality of reference. Locality of reference. What is this locality of reference? So every time whenever CPU performs any memory read, it will first search into the cache memory and then it will return to the main memory. So what happens that programs, whenever we are accessing some data, whenever we are accessing some data, then this entire data is not placed into the cache memory. The entire data is not placed. Why data? If I will place all the data from the main memory into the cache memory, then there is no need of main memory. There will be no need of main memory if I will place all the data in the cache memory. And I know that cache memory is having the higher cost. So if I am adopting the technique that instead of going to main memory, why I cannot bring the entire data? Is it not possible to bring the entire data placed in the main memory into the cache memory? So what will happen? What will happen if I will place the entire data into the cache memory? More number of cache will be required. More caches will be required. More caches, or the size of cache will be more. And this cache memory is costlier than the main memory. So if you will increase this cache memory, ultimately the cost of your computer will increase because cache memory is having higher cost. So for this, the thing is, we do not take all the data from the main memory. We do not take all the data. What we do, only the information which is required again and again is placed into the cache memory. Is placed into the cache memory. So this cache memory works on the principle of locality of reference, and the locality of reference says that many times the program consists of loops. Many times the program consists of what? Loops. So loops means if I want to access the information stored in the variable sum, and CPU is searching for this sum variable. CPU is searching for this sum variable in the cache memory. First time we perform searching for the sum variable. We searched in the cache memory and we did not found this sum variable. Then we will go to the main memory. Now we found that sum variable. We will take that this value sum and we will put it into cache memory. That means first memory miss occurred. First time when I search for this sum variable, one memory miss occurred. Now next time, the locality of reference says that the program always or many times we make use of loops. That means one variable is accessed many times. This sum variable will be accessed many times. So next time when I need this sum variable, I will not have to go. I will not have to move to the main memory. I can find it into the CM only. That means only into the cache memory. So next time when CPU will search for the sum variable, we will have next hit. We will have a next hit. Now third time, when the next loop, for the next iteration of loop, again I am searching for sum. Then again I will have hit. Again I will have hit. Yes or no? But first time when I am searching for sum, this sum was not in the CM. So what data I will bring? If the data is not there, if I am searching for some data, if that data is not there, I will search into the main memory and I will load that data back into the main memory. I will load that data back into the main memory. So this mechanism of bringing, first searching the data into CM, and if not found, then search in the MM. When found in MM, loading the data into the cache memory. This principle is called as temporal locality. Temporal locality. Why temporal locality? When this will be useful? When I am making use of loop. When I am making use of loop. So programs tend to refer to the same memory location at future point in time. So first time I need some, then it may happen that I will need some again, some after some point of time I will need some variable. So I know that if I need any information right now, that information will be needed again and again. So what I will do, I will put that data into the cache memory. This principle is nothing but temporal locality, or this principle is called as temporal locality. So this is first principle. पहला प्रिंसिपल हमने क्या देखा कि अगर हमने डेटा सर्च किया कैशे मेमोरी में, अगर वो वहां पर नहीं है तो मेन मेमोरी में सर्च करेगा. मेन मेमोरी में अगर मिलता है, मेन मेमोरी में 100% हमें मिलेगा ही. जैसे ही मेन मेमोरी से हमें डेटा मिलता है, हम उसे कहाँ लेके आएंगे? कैश मेमोरी में लेके आएंगे. तो अब नेक्स्ट टाइम अगर मुझे इस सम की जरूरत रखती है, if I need this sum variable, I will found it definitely in the cache memory itself. So there will be no miss ratios now. The second is spatial locality. What is spatial locality means? Again, it is always the case that if I need some memory location, if I need some data, then I do not only need that data, but I also needed the nearby place also. I also need the nearby place also. This is the second one. That is, program need to refer to the memory locations that are near to the other recently referenced memory location. So that means we do not every time, if I have a data structure in this way, let's say this is my memory address 10, the next memory address is 11, the next memory address is 12, the next memory address is 13. Then what data will be loaded? So let's say I want to access this 11. I want to access this 11. So what cache memory will do? What cache memory will do? This cache memory will not only bring this 11, but also the data placed near to it. Also the data placed near to it. That means it will also bring 10, 12 and 30. That means it will entirely bring this data complete 10, 11, 12 and 13. Why I am doing this? If I only need the memory location 11, if I only need the memory location 11, then why I am not bringing this 11 only? Why I am bringing this 10, 11, 12 and 13 also? So the thing is, again, the principle behind this is the principle of spatial locality. Spatial locality says that program always make use of arrays. We know what are arrays. Arrays are nothing but the continuous memory location. Continuous memory location. So many times it happens that if I need some information placed in the some location, then after some point of time I will need the information near to this. Near to this. So if currently my need is of memory location 11, then it may happen that in future I may need 12, I may need 13 or I may need 10. So again there will be memory miss ratios. If I will not bring 10, 12 and 13, then the memory miss will be more. So what spatial locality says that not only bring the 11 but also bring the data near to it. That means bring 10, 11, 12 and 13. That is the principle. This is the principle of locality of references. So there are two principles. Number one is temporal locality and number two is spatial locality. Temporal means what? Temporal means where if we make use of loops, then the same memory location will be accessed again and again, so I will bring that data into the cache memory. तो वो डेटा को मैं डेफिनेटली मेन मेमोरी से कहाँ लेके आऊंगी, कैशे मेमोरी में लेके आऊंगी. The second is spatial locality. This is useful. This is the this example or this principle can be explained with the example of arrays, where we have continuous memory location. So if I need memory location 11, it may happen that in future I may require memory location number 12, I may require memory location number 13, I may require memory location number 10. So again I have to go to the main memory to access that 10, 12 and 13. So why not to bring the entire data? Why not to bring the nearby ones also at the same time into the cache? So cache not only brings the required data, जो डेटा रिक्वायर्ड है मेन मेमोरी से, वो डेटा तो वो, here I am again summarizing this. So this is my cache memory and this is the main memory. This is the cache memory. So cache memory will not only whatever data is required by the processor, cache memory will not only bring that data, सिर्फ वो उसी डेटा को नहीं लेके आएगा, but it will also bring the data near to its places, near to its memory location. So it will bring entire data near to it. This complete data will be transferred from main memory to where? To the cache memory. This principle is very important, locality of reference. Next we'll see So we have seen the locality of reference. Next we will see the addressing, how the addressing is done, or what will be the size of memory, what will be the size of cache memory. Again, many times the question asked, many questions are based on this topic also. So here I am assuming that, or every time it is assumed that a is always main memory is always byte addressable. Main memory is always byte addressable. We have seen this in the very first lecture also. What is byte addressable? So the main memory is always byte addressable. Let's imagine that I have a main memory. I have a main memory. This main memory is able to store 2 bytes. इमेजिन कीजिए कि हमारे पास एक मेन मेमोरी है और इस मेन मेमोरी में कितने बाइट कितना डेटा रह कितने बाइट स्टोर कर सकता है ये मेन मेमोरी 2 बाइट्स. So here I am giving you this. Main memory is of 2 bytes. So this is my byte 1 and this is byte 2. Now if I want to assign, this is the memory, if I want to assign unique address to these memory locations, unique address to these memory location. I want to assign unique address to this byte 1. I want to assign unique address to this byte 2. Then how many number of bits will be required? This is the question. How many bits will be required for whom to give the address of, to give address to the main memory location के addresses को address देने के लिए कितने bytes लगेंगे? So there are how many bytes? Byte 1 and byte 2. Can I write that this is byte number 0 and this is byte number 1? This is byte number 0 and byte number 1. 0 is the address for byte 1 and 1 is the address for byte 2. So how many bits I needed? I need only 1 bit. I need only 1 bit. I need only 1 bit. 0 bit is used for, what is the address of byte 1? The address of byte 1 is 0. The address of byte 2 is 1. This is the address of byte 1. 0 is the address of byte 1. 1 is the address of whom? Address of byte 2. Address of byte 2. So if my main memory is having 2 bytes, then I need only 1 bit. I need only 1 bit. Now let's imagine the next situation. What if the main memory now this time my main memory is having 4 bytes. 1, 2, 3 and 4. So this time I'm having how many bytes? My main memory is having how many bytes? 4 bytes. So how will you assign, or how many number of bits? How many number of bits will be required to assign unique address for each byte? So if I will make use of only 1 bit, so here I will write 0, 1, 0, 1. अगर मैंने 2 ही बिट्स का यूज किया, एक ही बिट का यूज किया, एक ही बिट, कौन सी, आइदर 0 या तो फिर 1. एक ही बिट, वन बिट इंफॉर्मेशन का मैंने यूज किया, 0 या तो फिर 1। तो यहाँ पर जीरो जीरो एड्रेस पे आपको कितने बाइट्स मिल रहे हैं? अगर मैंने बोला कि जीरो एड्रेस का, सीपीयू बोल रहा है कि मुझे जीरो एड्रेस से डेटा चाहिए है, तो जीरो एड्रेस पे तो बाइट 1 भी है, और दिस इज बाइट 2, दिस इज बाइट 3, दिस इज बाइट 4। तो जीरो एड्रेस पे तो उसे दो वैल्यूज दिख रहे हैं, एक जीरो एड्रेस पे दिख रहा है B1 और दूसरे जीरो एड्रेस पे दिख रहा है B3। so it is making confusion. That means there is no unique address. There is no unique address. The addresses are being duplicated. The addresses are being duplicated. This means that this one bit information cannot be used for these 4 byte information. This is correct in this way. You can write in this, if my memory is 2 byte, then you can make use of 1 bit information only. Address can be specified in 1 bit only. But if the number of bits, if the size of my main memory is having 4 bytes, then these 1 bit information is not possible to represent the address. So let's try to have 2 bits. Of 1 bit, instead of 1 bit, let's try to have 2 bits. So how I will write here? I will write 0 0. 2 bits means how many combination? If I have 2 bits, how many combination will be there? 0 0, 0 1, 1 0, and 1 1. So here I am writing 0 0, 0 1, 1 0, and 1 1. So now you can see that the B1 is in the memory location. The address for B1 is at 0 0. The address of byte 2 is 0 1. The address of byte 3 is 1 0. Address of byte 4 is 1 1. So if I am having 4 bytes, then how much bits I required, how much number of bits I required to represent 4 bytes data? I require only 2 bits. I require the 2 bits. 2 bits are required for whom? 2 bits are required for 4 bytes of information. If my data is having 4 bytes, then I will require. So similarly, can I write this as 4 bytes? 4 bytes. This means 2 raised to power 2. 4 bytes data means what? 2 raised to power 2 bytes. 4 bytes means what? 2 raised to power 2. So this power 2 indicates the number of bits required to address the number of bytes. Required to address the number of bits. So how many bits I required? Power of 2. So 2 to the power 2. So this, how many number of bits will be required to address this? I will need only 2 bits. Now come to this example. Come to this example where I was having how many bits? How many bytes data? I was having 2 bytes. So 2 bytes can be read it in this way as 2 bytes can be represented as 2 to the power 1. 2 to the power 1. So what is, how many number of bits I required? This 1. So here this is number of bits required to address B1 and B2 will be 1. B1 and B2 will be 1. So let's take, this was the example of very lesser memory. Let's take a big example, a main memory which is having a large size. So let's say that I am having a main memory. I'm having a main memory which is of 64 MBs. The size of my main memory is 64 MB. So how many bytes I have? 60. The data, the entire data is 64 MB. So you can note down the four things in short: 1 KB, then 1 MB, then 1 GB, and 1 TB. You can note it down. 1 KB is nothing but 2 raised to power 10. 1 MB is nothing but 2 raised to power 20. 1 GB is nothing but 2 raised to power 30. So if I say that 1 KB, my memory size is 1 KB. So this actually means 2 raised to power 10 bytes. 2 raised to power 10 bytes. If I say that my memory is 1 MB, then it is actually 2 raised to power 20 bytes. If I say that my memory is 1 GB, then it is 2 raised to power 30 bytes. If I say that my main memory is 1 TB, then it is 2 raised to power 40 bytes. 2 raised to power 40 bytes. So you need to note this. This is very important. 1 KB, 1 MB, 1 GB, and 1 TB is equal to how many bytes? So the question was, if I am having 64 MB, 64 MBs का information है main memory में, how many bits I will required to represent or to write the address of this 64 MBs data. So we will write it 64 MB. So write this 64 as it is. 64 into MB. 1 MB is nothing but what? 2 raised to power 20. So here I am writing 2 raised to power 20. So this 64 MB can be written as 64 into 2 raised to power 20 bytes. Because 1 MB means 2 raised to power 20 bytes. So here I am writing 64 into 2 raised to power 20. Now write down this 64 again in the power of 2. How will you write 64 in the power of 2? It is 2 raised to power 6 into 2 raised to power 20. 2 raised to power 6 into 2 raised to power 20. So what will be the answer? 2 raised to power 20 plus 6, this will be 2 raised to power 26. So 64 MB is nothing but how many bytes? How many bytes it is? 2 raised to power 26. So if you know the power, if you know this, then the number of bits required to represent its physical address will be how many number of, what will be the number? 26. So the address for 64 MB will have total 26 bits. Will have total 26 bits. Similarly, you can solve for the question. For 4 GB, let's solve for 4 GB. 4 GB. What will be the number of bits required to represent the address of this 4 GB memory? 4 GB, this is main memory. What is the size total? It is 4 GB. So how many bits will be required? How many bits will be required to represent each address? I got the answer here, that is 32. Very good, Pranjal. So we'll stop it here itself.